Hello and welcome to today's webinar presented by Delubal Software. Today we'll be working in our structural analysis and design software, Rfem. The topic for today's presentation is Aisc 360 2022 Steel Connection Design in Rfem 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and also a technical support and sales engineer, and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Cisco Cho will be your moderators, answering any questions you may have. They are both technical support engineers, also located in our Philadelphia office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the presentation. You can do so within the same dialog box. If by chance we don't get to all your questions, we'll certainly send you a follow-up email afterwards. So to quickly go over the content that we'll cover over the next hour today, I do want to give a brief introduction to the steel joints add-on for connection design within our FEA program, Rfem 6. We'll talk about the applicable Aisc 360 and the new 2022 standard updates relevant for Rfem. Then we'll go on to discuss the new components and features that are now available within the steel joints add-on. And finally, we'll run through our example model shown over here on the right-hand side to talk about the connection input data and workflow. We'll run the analysis and the design and talk about the results. So for those of you not familiar with our programs, Rfem 6 is the base software program. So this allows us to fully model the global steel structure. We can load it. We also have the ability to integrate with BIM software. And from here, we'll get the full analysis. Now, we want to take this a step further to carry out the member design according to the AISC, then we would need the steel design add-on. So this was our focus last week in the first part of this two-part webinar series. So I'd certainly refer you back to this recorded webinar on both our website and YouTube channel if you are interested to learn more about the actual member design according to AISC 360 or 341. But today we will be focusing on the steel joints add-on. So within this same Rfem model, we can then carry out the connection design according to the AISC. I also mentioned here the structure stability add-on. This is needed if we wanted to carry out an eigenvalue analysis for our connections to determine the various buckling mode shapes, which we'll see in our example today. So our steel joints add-on is a bit unique in the sense that for every single connection, we are going to generate an FEA model underneath the hood. So we might be wondering, what is the benefit of FEA for steel connection design when we compare it to standard analytical calculations? The first and probably most obvious is that we can now design these non-standard connections. So we're no longer limited to standard beams, to columns with maybe one or two braces, but rather any connection that can be created with these various components can be fully designed according to the AISC, such as the example that you see over here on the right-hand side. This does include components and members both in plane and out of plane. So we're not restricted to the design in a single plane, but rather we can include all of these elements at one time for the full design. We also can consider complex loading because we are integrating the full global Rfem steel structure with the connection design. We have the ability to consider all of the loading within Rfem itself. So whether this is member loads, point loads, perhaps we have it integrated with surfaces and those surfaces have additional loads. This is all considered with the connection design with the automatic member end force transfer. We also are automatically generating what we call this submodel underneath the hood. So it really doesn't require a high expertise level. Rather, if you just have a general knowledge of FEA, because of this automation, this will all be done automatically. We also create an additional second submodel for the buckling analysis to carry out that eigenvalue analysis. Oftentimes, an eigenvalue analysis can be very difficult to calculate by hand, for example. So by utilizing FEA, we can certainly take a look at the buckling behavior itself. We also now have the ability to calculate and classify the connection stiffness. Now, where this is a benefit is that we can then modify our global model to account for the true connection stiffness properties, which are inevitably going to affect the internal forces with the analysis. So all in all, we will have more precise results with less assumptions, especially for these non-standard or very complex connections. Even if we're using hand calculations or we're using some type of external program, Rfem and the steel joints add-on can still be a great validation tool just to confirm that our assumptions are correct. So let us talk more about this submodel that's automatically generated, and we can see an example shown here on this slide. So all of the members, so talking about beams, columns, braces, these 1D member elements are automatically converted to 2D surface elements in this submodel. So we're talking about the flanges as well as the webs. These will all be converted to those 2D surfaces considering the correct thickness and the material. We also consider the bolts and welds. These are also converted into 1D and 2D elements in this submodel. Now, in the Rfem model, we likely have defined here linear elastic materials for our members. In the submodel, this is automatically converted for all those surface elements to nonlinear plastic materials instead. So no additional add-ons are needed for this. It is automatically done with the steel joints add-on. Additionally, we'll see geometric nonlinearities applied automatically in the submodel. So for example, with two end plates, we should see those plates release in tension, but in compression forces, we'll see them bear upon one another. Again, we talked about automatic member end force transfer. So all of the load combinations, such as according to the Aisc E7, are automatically brought into this submodel as member end forces, and we'll run through the separate calculations for each load combination. Now we are getting full design according to the Aisc for our plate, bolt, and welds. We'll see this in the design results within our example. As mentioned too, we create a separate submodel for the buckling analysis. So what this is going to tell us is the various buckling failure modes that we can graphically see, as well as the critical load factors shown in table format. And finally, obviously a big benefit here is the integrated member design all within one file. So turning now to the Aisc 360, the new 2022 updates that are relevant for Rfem only. And so we're talking about specifically connection design. This list is rather short, just one simple section here to consider. Section J 2.4a for welds and welded joints, in particular the fillet weld strength calculations. There were some clarifications and revisions made to section J 2.4a and b. And the main reason is because we have adjusted this equation J2-4 for fillet weld design to now include this directional strength increase factor K sub ds. And K sub ds is calculated according to equation J2-5 unless we have a rectangular HSS, and in that case this value should be set to 1.0. We will see this reflected in what we call the design check details in Rfem that you see over here on the right hand side for all fillet welds. So now moving on to a few of the updates that we have implemented in the steel joints add-on over the last year. So this isn't an exhaustive list, but rather I just wanted to focus on a few of the main points. The first is the preloaded bolt input option. So now we have the ability to consider these preloaded bolts where the submodel then automatically will include the applied bolt pre-stress force. In addition, we're going to see an increased surface friction coefficient for those plates that are in contact. Now, the load pre-stress within that submodel does come from Aisc table J3.1, and we're going to reference that 0.7 factor times the bolt tensile strength. So the advantages of a preloaded bolt or slip critical connection really increases the joint rigidity and tightness. Also, we're going to see that increased contact stress in the plates before additional loads have been applied. If we have a high vibration environment, we're obviously going to see better control of the loosening of the connection and other benefits. We also now calculate the connection stiffness and further classify this. So we have the ability in the steel joints add-on to calculate the rotational and axial stiffnesses for each member that frames into that connection point. So two values for each of these are going to be provided. For example, if we take a look at the stiffness of the strong axis bending rotational moment, we will see two values here, a positive and a negative, and this is just depending if the member is in positive bending or negative bending. Now, if we have a completely symmetric connection, these two stiffnesses would be identical. The further classification for rigid, pinned, or semi-rigid comes directly from the AISC, figure C, B3.2 and B3.3. So we see that given to us in table format in the results as well. Now it is planned for the future to automatically export back out these stiffnesses to the global model in Rfem, which again are going to affect our member design with the internal forces. For now, we can manually consider that, which I'll show you at the end of our example today. We also can now consider round HSS connections. Previously, this was a small limitation that we had. So these sections and wells are analyzed using the segmentation method, and we'll take advantage connection today with Juicy in the upper right-hand corner with these round HSS members. A few components and capabilities that we have also added. Inserted member is a new component, and this might be important for connections with stubs, or perhaps we have fly bracing, intermediate connection pieces, and so on. Another component that we've added is called auxiliary solid. So sometimes with plates or members, we require some modifications that are rather complex. So these new auxiliary solids with boxes, cylinders, or sections allow us to make these modifications, such as a plate cut, again, for more complex geometry. We also have added a cap plate. So this automatically positions a plate with the correct dimensions and weld definitions, for example, to the top of a member. We have a new rib component. So this is a quick stiffener element that exists between two plates. And this is just really going to reduce what previously took many other components to create. So a much more efficient option now. We also have the connecting plate notch member. We'll see this in our example today. Also with the same connection here, we can automatically weld the connected members to the gusset plate through member notches. This will be a very efficient input as well that we'll see. We have added measuring tools within the steel joints add-on. So now you can right click in the joints view to activate these measurement tools. If you just need to make a quick measurement graphically, this can be very useful. And finally, this probably won't be so apparent in Rfem itself, but in that submodel, we have added some additional nonlinear line and nodal releases for contact edges. So for example, if we have a beam splice where these two edges are butting up against each other, you'll now see in the submodel that in tension, we will see these two elements separate away from each other, but in compression, we'll see full force distribution between the two elements because of these nonlinear line and nodal releases. All right, so we will move to our Rfem example today. So for those of you who joined us last week for the full member design according to the AISC, this is an identical model here. I again will refer you back to that webinar to learn more about the member design, but let us quickly go through just a quick model review. So for the cross sections, we do have W12 by 50s for our columns, W18 by 40s for our girders, W16 by 31s for their smaller transverse beams. And then for our X braces, we do have round HSS members, 4-inch diameter by 0.25-inch thickness. As far as the loading, this is also identical to last week. So we have 4 very simple load cases for today: dead, live, wind in the X, and wind in the Y. Now I did make one minor modification here. When we compare to last week's model, you'll see here that for dead load, we do have the surface loads applied to the surface load transfer elements, but I did apply additional member loads that you'll see here to those girders. I wanted to see a little bit higher internal forces and stresses with our connection design. Additionally, same concept here for live load, that we have these surface loads applied, but I have also added a couple of point loads at 2 points along those transverse beams as well. We also have wind in the X direction, taking advantage of our load wizard here. We can right click to display those. These are just distributed to the members based on their tributary area. Same concept here for wind in the Y direction, and we can right click here to display those as area loads instead. Now, we also talked about last week how we are generating the load combinations automatically according to the ASCE 7, the new 2022 standard. Under the design situations, a program will automatically create 2 design situations for us. The first is going to encompass all of our factored load combinations. So this comes again directly from the ASCE 7. The second design situation includes all of the unfactored load combinations. And we use these for the strength and serviceability design of our members utilizing that steel design add-on. Now for our connection design, we're only going to utilize this first design situation. Under the load combinations, if we'd like to see those individually listed out, we see our factored load combinations here in orange and our unfactored load combinations in red. And to quickly revisit to the steel member design, I will go to the table here and drop down to the steel design add-on. If you remember from last week under the design ratios by member, ultimately we are going to get full member design here. And if I click on this back girder, you'll notice that all of our design checks from the Aisc 360 are listed here. And for each one of these, we further have the ability here to take a look at the design check details. So this is going to show us line by line with these various formulas, along with the code references, the relevant design ratio that we're going to get again for the member design. So once we feel comfortable here with the member design, what we would like to is the connection. So I'm going to go back to the navigator and I can right click on my model name to access the base data dialog box. This is also available up here in my toolbar. Within this dialog box, under the second tab are the relevant add-ons that we have available within Rfem. So we've already taken advantage of the steel design for the steel member design, but now we would like to activate here the steel joints for our connection design. And under the fourth tab is where we would set the relevant standard to the AISC 360. You'll notice here we do have the 2016, but we also have the most recent 2022. So once this add-on is activated, we're now ready to define here our first connection. So I'll go ahead and turn off my surfaces graphically just so that we can see our members in better detail. Because we have activated here the steel joints add-on, we have a new folder within our navigator called types for steel joints. So I can right click to create my first definition. Now, I'm going to graphically select my node here and we're going to focus on our beam to beam connection. So we just simply click on graphically node number 34. We see the relevant members highlighted here in our view. And under the second tab are the listed members. So you'll see here that we have 2 members within our table, and under the second column is the type set to continuous or ended. So member number 1 in the rear is set to continuous because it is continuous through this connection point. Now, alternatively, we have our second member here that is set to ended because it does end at this connection point. Because we are generating the FEA model automatically underneath the hood, we do need to support at least one of these members at the member start or member end at a minimum. The program will go ahead and suggest that it will support our member number 1 at the start. So then we have our components. So we can individually insert in the connection components here. You can see the different categories where I can insert in a plate, or perhaps I have a haunch, or maybe for this connection, we will take advantage of a cleat. Now, alternatively, we can also utilize our library. So if we launch the library, What you will further see are some various connections already defined for us. And we have rigid connection under the general categories. We also have pinned. We have truss connections as well as brace connections. So looking at our general pinned category, we then have further subcategories like beam to column. So when we look at beam to beam, we have 3 additional options, including a cleat. So we can hit apply template, and the advantage of this is that these components that are already defined within this library will automatically be applied to my model. Now, when I look at this preview, I actually don't see my cleat generated, and that's just simply because I need to switch these 2 members within the dropdown. My continuous member is actually member number 1, and the member that ends at the connection is member number 2. And now we see this cleat generated graphically for us. We also can select here the material of the cleat. Now it's possible to also define this later on under the individual component, but if we have our material available, we can select it here from our dropdown. Alternatively, if we do not see our relevant material, we can choose the new material option here. This will allow us to launch our material database, where we can use our filters on the left to filter to the United States, to steel, and to the new AISC 360 2022 standard. And pretty much every material should be available here. You'll notice there are additional subcategories as well. So once we find our relevant material, we could select it within this material library. Now for my scenario, I already have the material defined, A36 for structural shapes. I'll go ahead and select it here. So when I click OK, you'll notice that this component, again, was automatically brought in here into my table. We will need to make further geometry modifications because, again, this is just generalized to bring in the component, but we need to set it up specific to our model. The first thing to define here is the offset between the 2 members. So we're talking about this gap here. I'll go ahead and reduce this to 0.25 inches, and we graphically see that update. Now the material for the cleat has already been defined, but again, we can make changes if we'd like. The cross section for the cleat, if you'll notice here, this is automatically set to a parametric section where we can input in the dimensions. Alternatively, if I hit this back button, I can take advantage of the standardized sections directly from the AISC. You'll notice the 16th edition database, which is the most recent, is implemented here. And I can go ahead and select a single angle 3x3 by 1/4 inch thick. So I click OK, we'll see that cross section automatically update here. Now, rather than defining the offset, I'm going to define the length and the position. So the length of this cleat is going to be set at 10 inches. The eccentricity will be set to 0 so that it's simply centered at half the depth of the beam. Now we want to move on to our bolts. So we'll begin with the bolts on the left, where we will set these as A325, 1/2 inch diameter from our drop down. Currently there's 2 bolts defined, but I'm going to increase this to 3. The second input settings are the spacing. So this is set up to specify the distance from the top of the cleat to the center of the first bolt, then the center of the first bolt to the second to the third, and so on. So my spacing from the top of the cleat to the center of my first bolt is going to be 1.625 inches. I then hit the space bar on my keyboard, and I'm going to input in the spacing from the first to the second bolt, 3.375. I hit the space bar once again. I'm going to input in 3.375 yet again for the second to third bolt spacing. Now I do not need to input in the distance for that 4th spacing. The program is intelligent enough to know what that distance is, so it will automatically be input. Now the number of bolts in the transverse direction are set at 1. If we want to modify the spacing from left to right here, we start off with the space from the edge of the cleat on the left to the center of the bolt, and this is set at 1.375. Again, if I just hit enter, the program will recognize the distance to the center of the cleat here automatically. We talked about in the PowerPoint the new ability to specify here if they are pre-tension bolts for this slip critical connection. This is a simple checkbox here that will affect the submodel. It's not applicable for our connection, so we'll go ahead and leave this unchecked. We also have the ability to define if the shear plane is in the thread. So ultimately, this is going to affect the bolt strength in our calculations. This is a simple checkbox as well. Then we move on to the bolts on the right-hand side. So we will also specify here our 325 bolts, 1/2 inch diameter. We're going to increase the number to 3. Now, as far as the spacing, it's relatively easy to go back to the left side. I hit Control C on my keyboard, and then I can hit Control V to paste that to the right-hand side. So I don't necessarily have to manually input that in if we want to replicate the spacing on the left-hand side. Same concept here for the spacing in the transverse direction. We can go ahead and copy and paste there as well, and all of that will be updated graphically. Now, our cleat is complete with all of our input. If we go to the plausibility check, this is going to flag us if we have any errors within the connection. So remember, we are generating this FEA submodel underneath the hood. So if there's any errors such as overlapping elements, perhaps a bolt is not placed where it should be, then the program will go ahead and flag you of this. Otherwise, the submodel cannot be generated. In our case today, we have a couple issues telling us that the flange and the web from the smaller beam is conflicting here with the flange of the larger beam. So we go back to our components and we need to add in a new component here. And what we want to select is called Member Editor. So you can see how we can use the library options to bring in a starting point for a connection, but we can always add more components, we can delete components, or we can make modifications to those existing components. Now, with this Member Editor, what you'll see here is that we do want to select member number 2 within our dropdown. And rather than specifying a chamfer, we will select a notch, and we need to give the notch some dimensions. So I'm going to choose here 0.75. I hit the space bar by 3 inches. We also have the ability to add in a rounding here for our radius input. So we'll set this to 0.375. And we'll see that rounding affected graphically. And lastly, the program asks us if we want to apply this to both the top and the bottom. There really is no need to apply it to the bottom here, so we will just select side number 3 only. So now we see that notch. We should check under the plausibility. There are no errors found, so therefore we've taken care of any issues there. If you want as well, just to show you that if we right click, we can take advantage of that new measure tool. For example, we can choose the distance between 2 points, and the program will allow us here to snap from one point to another. Graphically, we'll bring up this separate dialog box. This will show us just further information about that particular measurement. It might be helpful again for any input that we want to place within the component itself. So now that we are done with this first connection, we click OK, and we're brought back into the Rfem global model. And you'll notice here that my connection is displayed graphically. So we have the ability here to also turn this to wireframe while still displaying this connection. That I just wanted to explain that the full member design is still carried out from node to node. We're not going to maybe stop this member here where the connection design begins, but rather the full member length is considered. In addition, the member end forces are taken at this specific node. They're not taken at this short distance away from this connection point. So this is really just a general view of that submodel that will be created again in the background. You also have the ability here, if we go back to, I'll keep this in wireframe view, you'll notice that we have a new option here to show no joint model. If we wanted to completely hide it, we also have the simplified option here, or we can go ahead and keep it as a detailed joint model. So this particular connection is also applicable to many other locations on this structure. Well, you don't necessarily need to redefine the connection each and every time, but rather we can select multiple nodes to apply it to. And this also is true for the other side of the structure, even though these elements are mirrored, as long as the geometry, the members, everything is identical, this same joint can be multiple nodes. So we go ahead and double click on it, and to take advantage of that, we can select here some of the adjacent nodes that again have identical geometry. So we select nodes number 35 through 37. We see them selected here in the graphical view. I click OK, and we'll go ahead and turn this to a solid view. We see those connections shown at each one of these locations, probably even more clear in the wireframe view. So we are now complete with this first beam to beam connection. We want to then create our second definition here for our X-brace connection. So we right click to yet again create a new steel joint definition. We can still refer back to our previous one, but now we will select graphically here node number 77. We click OK, we see the relevant members highlighted, and under the Members tab, we see that all of them are set to the type ended, and that's just simply because all of these members will end at this connection point. We do need to support at least one of those members for the FEA submodel, so we'll leave this as the default for member number 1. Under my components, this is where I actually want to add in the individual components rather than using my library. So we will begin here by first inserting in a plate. We give the plate a material that's already available here within Rfem. So I select it within my dropdown as A36 for plates. The thickness is left as a default here, 0.375. The width will be adjusted to 13.75. And the height will also be 13.75. We see this adjusted graphically here as well. But clearly we need to make some modifications to this plate rotation. So we can turn on the local axis system of the plate itself. Therefore, I am going to rotate it 90 degrees about the plate's local x-axis, and I'm going to further rotate it 45 degrees about its local y-axis. So we'll go ahead and turn those local axes off, and now we see a little bit better orientation here for the plate element. We then move on to our second component, and this one is going to be the plate editor. So we want to apply this to plate number 1. It will be a chamfer, and the dimensions of this chamfer are going to be 3 inches by 3 inches applied to all sides here. And so now we just see that quick geometry change applied graphically. We then add in our third component, and this one is going to be of the type connecting plate. But as mentioned in the PowerPoint, this is a new feature that we recently added where I can select here member number 1. And we have the drop-down option to create a notched member with a tongue plate. So if I rotate this around, you'll notice that this tongue plate was automatically created, attached to this bigger plate here by means of bolts. We added a notch into the member, so we've significantly reduced the number of components that it previously took to generate this. Now moving on to the plate element itself, we want to adjust here the material to A36 as well. The thickness for the tongue plate will be left at 0.375. We want to adjust the offset though to 3 inches. The remaining width is going to be set to 6 inches, and because I set my total X indentation to 9 inches here, and then we also see the overlap in the remaining width set at 3 and 6, the program is intelligent enough to set automatically the width to 9 inches. So then the height is going to be adjusted to 4.75 inches. Again, we're just affecting the geometry here of the tongue plate itself. It will be attached here to our larger front end of the plate. We can also select the weld to be applied to the notch. So when we turn on this option, we'll see the weld applied between the member and the tongue plate. We can set the strength of the weld to E70 with the throat thickness also input here at 0.125 inches. Then we finally just need to adjust our bolts. So these are set as A325, 1/2 inch diameter. We do have 2 bolts in the horizontal direction. We need to input in the spacing as well. This is going to be from the top of this tongue plate to the center of the first bolt. So we'll set this distance here as 1 inch. I hit my space bar. The distance between the first bolt to the second bolt will be set at 2.25 inches. I hit enter. The program will automatically determine what that third distance should be. Now the spacing in the vertical direction, this is automatically centered on the tongue plate, so we don't need to do anything further here. So now that we are done with this component definition, it's easy enough to right-click here to make a copy of this component at the end. So we're simply copying everything that we've just defined, but we're going to do it a total of 3 times because we have 4 different members framing into this connection. So under my second connecting plate component, I'm going to scroll up, and rather than selecting member number 1, we want to change this to member number 2. The only adjustment that I will want to make here is to modify my X indentation to 9 inches. And we'll do so the same thing for our third connecting plate by changing this to member number 3. And we will automatically adjust here the X indentation back to 9 inches as well. And finally, we're going to do it this 4th time here for member number 4. And we will, for the last time, adjust here that X indentation to 9 inches as well. So essentially, our connection design component input is complete. We can jump here to the plausibility check. We don't see any errors found. We now have the ability to save this connection to our library as well. So we could give it a name, we could select the category, or if you leave this as empty, this will be placed in your user-defined category. Instead, we can create additional subcategories, or you can notice here that I've already created the category X joins. So it's really encouraged to save these connections to your library so that it's now available for any future Rfem models. You can pull that open, all of these components will be brought in, and you can just make simple changes then to the component input. So we go back to the Rfem model here. And what we should see is the display now of this connection graphically. So we'll turn this to a rendered view. And sure enough, it's displayed here at our X braces. But remember, in wireframe view, we still have the design of these X braces to that particular node here. So the full member length, this is just a representation of that submodel. So we're now ready to create our third and final connection, and that's going to be for this node here where we have 2 beams, a column, and a brace framing in. So a little bit more complex than what we've seen with the other 2. For the last time today, we will right-click to create our new steel joints definition. This time we want to select here node number 2. So we see the relevant members brought in here, and again, all of them are set to ended with the relevant supported end here set by the program by the default option. Now, to individually input in these components will take a little bit of time. So what I went ahead and did is created this connection and saved it to my library. So we'll launch our library here, and under my user-defined category, I have my specific subcategory where I can simply hit Apply Template. So you'll notice that all of these components have been automatically generated, saved to the library, and now we're applying it to my specific model today. All of these components are listed here with the relevant materials. If we needed to change around the members, we could do so, but everything should be set for this example. So I click OK, and you'll notice all of these components automatically input here. Just to touch on a few of those new features that we talked about in the PowerPoint, we'll zoom into this connection. So we see a nice rendering of the connection itself. The cap plate is a new component, so you can see this cap plate automatically inserted at the top of my column. You'll also notice it's not standard rectangle or square, but rather we can make some geometry modifications to it as well. You'll also see here the new component inserted member. So it's probably best if I go ahead and hide a few of these components, such as the member number one or column. Maybe I'll hide my cap plate as well. This inserted member is a upside down T-beam here that is welded directly to the column web, and it extends out, and we connect it with a plate-to-plate connection here back into the beam. So I just wanted to point out one of these new components available within the last year that we have implemented as well. So once we have input in all of the components, check the geometry, we would jump to the plausibility check, no errors found. This is great. We click OK, and we're yet again brought back into the Rfem model so that we can see just a graphical representation here of that connection. So I'll go ahead and rotate this around. We'll zoom in here, and we see all of our components graphically represented with the global model. Now, before we run the calculation, let us go back to the steel joints add-on. And we have here these strength configuration settings that are for each one of these connection definitions. Well, if I go into the detail settings here, the first thing you'll notice is the ability to carry out the buckling analysis. So again, you need to have the structure stability add-on to have this capability. So if you do own it, you can go ahead and turn this on. We get a new tab here where we can carry out that separate submodel. We will have the ability here to specify how many eigenvalues to calculate. This is set at 4 by default. We also have some other settings specific to the design check. So you'll notice here the plastic strain limit is set at 5%. So this is a really important topic and is often asked about. So let us go back to the PowerPoint to explain this a bit further. We are going to check the plastic strain limit. And for our plates, this is relevant for our flanges, our webs, any of the gusset plates we've defined, haunches, and so on. Because remember, in the submodel, these are converted to 2D surfaces. Now, we probably have initially defined these as linear elastic materials, but again, in that submodel, they're automatically converted to nonlinear plastic materials. With this material model, we will apply the von Mises yield criterion stress failure hypothesis. So taking a look at the stress strain diagram in the lower right-hand corner, you'll notice that below the yield strength, we have our linear elastic region. But once we reach that yield strength, Fy, we are now in the plastic region. So for a standard steel material, you'll notice here the physical stress strain curve is indicated by this red dotted line. Well, for the von Mises yield criterion within the program, we're actually going to simplify this just to a linear line here. Now we know the slope in the linear elastic region is just set to the modulus of elasticity E. For the slope here in the plastic region, we set this to the plastic modulus of elasticity, and we calculate this by just taking the modulus of elasticity, the linear modulus of elasticity, divided by 1,000. In that submodel, we are going to utilize the plastic behavior of steel with internal force redistribution. So what this means is that the load is going to be applied in this connection submodel to all of our Fe elements. And when that Fe element maybe reaches the yield strength, Fy, the load is distributed to the adjacent elements, and it's done so until the load has been fully distributed. So it could be that some of these elements have yielded. Now, in a particular connection model, we will have hundreds, if not thousands, of Fe elements. So we might be wondering then, well, why aren't we checking the stresses for these plates? Why instead are we checking the plastic strain limit? And the reason why is because if a couple of these FE mesh points are fully yielded out of thousands, we really don't want to flag the user that the entire connection has failed. So rather, it's better practice to check the plastic strain limit. So this will allow slight yielding of the connection without flagging it that the entire connection or that entire plate itself is failing. And we see this indicated here in the stress strain diagram. So we set this limit plastic strain, again, follow this dotted line up to allow partial yielding. Now the default here is set at 5% for that plastic strain limit. This comes directly from the Eurocode with the section listed here. When we reference the Aisc, there is no specific reference to what the plastic strain limit should be set to when we are considering FEA modeling for connection design. So therefore, we do refer to the Eurocode, but this is fully adjustable in the program. Now, there have been many studies that have been carried out for actual steel plate behavior compared to this FEA approach, and there has been found relevant correlation, so therefore it is an accepted approach. So we go back here to the steel joints add-on, and again, that 5% can be found here, but it is fully adjustable by the user. We also have the slip coefficient for slip critical connections, as well as the bolt pretension factor. So remember, this is for those preloaded bolt options. The 0.7 factor comes directly from the AISC table J3.1. So once we have input in all of our configuration settings, the final thing to do here is to talk about the stiffness calculations, which I mentioned was a new feature that we recently added. So taking a look at our last connection here, the more complicated one, you see this new ability to carry out the stiffness analysis. Now, we do have a configuration setting here that's default, so we'll go ahead and select that and take a look at it. You'll notice that we will calculate the initial stiffness of this connection for the relevant members. Out here, and that's just simply because they are still in work, but they should be available in the coming weeks. In particular, the ability to export out this stiffness back into the global model automatically. So because we have activated this under our second tab for our members here, if we scroll in to this connection, I'm maybe interested in calculating the rotational stiffness for strong axis bending of member number 2. So framing into the flange here of my column. Therefore, because I've activated the stiffness analysis, I have a new column here where I can calculate the axial stiffness, the rotational stiffness for strong axis bending, or rotational stiffness for weak axis bending. For this one, I'm going to activate only strong axis bending. So once we have this set here in the column, we see it populated. And we finally can jump here to the steel joints add-on within table format. So similar to last week's webinar, looking at the steel joint design, we have our design situations listed. And we are only going to deal with here the factored load combinations from that first design situation because we want to set this to the strength limit LRFD design. Now, a lot of these others, other than possibly ASD, are going to be irrelevant and more applicable to the member design. Same concept here for serviceability or unfactored load combinations. This isn't relevant for connection design, so we just leave this unchecked. Under the objects to design, we will design all of our connections that we have defined today. So this does take several minutes to solve. So remember, we're generating these FEA models underneath the hood for all of the ASCE 7 load combinations. Therefore, I will jump to an already solved for model here that we can take a look at our results. So once that calculation is done, we jump to the steel joints design here, and we have 3 different options to view. So we'll begin with the stress strain analysis. Zooming in here to my various connections and taking a look at the design ratios by node, you'll notice that each one of my connections is available in table format. And if we take a look at our corner connection here, we have 3 different options, including the plate checks, bolt checks, and fillet weld. So if we launch the design check details for fillet weld, this should look very familiar because we also have these design check details available for the member design in the steel design add-on. But ultimately what we see here are the equations relevant for the weld design listed line by line with the code references and our final design ratio. You'll also notice that new case of D. Oops, sorry about that. You'll also notice that the directional strength increase factor is given here within these calculations. This is new within the 2022. We can toggle to the fasteners if we like, rather than going back to the table. So you can see the bolt checks are given here line by line as well. And ultimately the controlling design ratio is shown here at the end. Now for our plate checks, it would be best to take a look at what we call the result in steel joints preview. So this is going to launch here that FEA submodel that we can graphically view. And under the second tab, you'll notice that the plastic strains are shown here. And really there's not a whole lot going on with. So therefore, if we toggle this to the equivalent stress, it might be a bit more interesting to us in that we can see the various stresses and where we have higher stresses on this particular connection. Additionally, under this first tab, if we collapse some of these options here, we have the ability to hide all of the members and plates. And perhaps we're interested in just seeing the stresses in the weld elements themselves. Or you can see here the tension forces within the bolt elements. You also have the ability to save this submodel to your computer. So you can then open it up like you would any other Rfem model. So to quickly show this, if we jump to this model that I went ahead and saved for this particular connection. Now, again, this isn't required. It's just if you want to save it and to open it up in Rfem to take a look at what's going on underneath the hood. You'll see here that FEA model fully modeled out here within Rfem, including the nonlinearities, both material and geometric, as well as all of our different ASCE 7 load combinations here. So those member end forces are automatically brought into this submodel. So you'll notice as I scroll through these different load combinations, those member end forces are going to automatically update here. Now going back to the steel joints model, we have now covered the steel joint results for the stress strain analysis. Remember that we've also carried out the buckling analysis because we've activated this under our various configurations. So with this in table format, we're going to see here our relevant connections. And for each one of these connections and nodes, we also have each load combination listed. So for example, taking a look here at my factored combinations for the gravity loads, dead plus live, and I'm currently looking at node number 34, which is going to be our connection here, our beam to beam. We have 4 different eigenvalues that we have solved for, and for each of these 4 different eigenvalues, we're also given the relevant critical load factor. So very similar to the stress strain results, we can also activate here the results in the steel joints for the buckling submodel. So we're probably interested to view what the various buckling mode shapes are going to look like for this. So here we see our beam to beam connection. And again, separate submodel from the stress strain, in that we're only carrying out the eigenvalue analysis. Under the second tab, we can slightly increase this factor to see that possibly our web is going to buckle as one of our first failure buckling modes. We can also save this model just like what we saw with the stress strain if we're interested to open that up within Rfem as well. But ultimately, for each one of these eigenvalues, I mentioned the critical load factor. So this is going to be the factor that we can multiply the loads in load combination 2 before we're going to see our connection fail with that particular buckling mode shape that we just saw with the web. So obviously, the lower the critical load factor, the more concerned with buckling we should be. The program can flag you at a specific value, input in the configuration of what the critical load factor should be if it's not passing this, and then we could decide if we want to put additional stiffeners in for this connection. Now, the final results are going to be that stiffness analysis. So here in table format, we see the connection stiffness calculation carried out for, remember, our connection here, but only for member number 2. And we had set in the configurations for only the strong axis rotational stiffness to be carried out. We see 2 values here, a positive and a negative value. And these 2 values are different because it depends on if this member is in positive bending or negative bending. Again, if the connection was symmetric, we would see the same values here. But in our case, it's not symmetric, so we have 2 different values shown. Furthermore, under the second tab is the classification. We can see here how this was classified. It was both set to semi-rigid in the case of positive or negative bending. So therefore, I want to take this value here and apply it back to my global model. So taking a look at this particular member, I want to hide the joint model, and I'm also going to turn this into wireframe view, but we only want to show here this particular member shown graphically. And I'm going to back up and go to the static analysis with all of my various load combinations. So under my navigator here, I'm viewing my results. I toggle this to the static analysis instead, where I'd like to turn on the member internal forces for bending. So taking a look at my factor load combinations here, as I scroll through these, you'll notice that we have negative bending connection point. So therefore, if I wanted to consider the true connection stiffness, I need to take the value back here under the steel joint design, and we want to toggle back to the stiffness analysis. I want to take this rotational stiffness with the negative bending moment value provided here. So we can hit Control-C to copy this value here. I go back to the global Rfem model. Now, by default, because I have not set any member hinges for this, the program considers this a fully rigid connection by default. So therefore, we're going to activate here a member hinge definition, and I get a new tab where I can define a new member hinge. This will bring up the dialog box, which has 6 degrees of freedom for this member in fixity. Well, we're only concerned with here the rotational degree of freedom for strong axis bending. So this is going to be in the local Y direction. Now I can hit Control-V to paste that value here into my spring constant. So now we are correctly accounting for the true rotational stiffness here, negative bending of this connection in the global model. So when we click OK, we see that hinge definition applied here. We click OK, and inevitably all of my results will be deleted here. And that's because we have this new member hinge defined. We would want to rerun the static analysis because what we will see now is a different value for our internal forces, again, now that we're taking into account that true connection stiffness. So it's planned again in the future to have the program automatically export these out as member hinges, but for now, if you do want to account for it, it's easy enough to apply that manually. All right, so let us go back to the PowerPoint to conclude today. I do want to end on a few future developments that we plan to implement in the near future. So these aren't necessarily longer term developments, but ones that you should see in the very near future. The first, as I mentioned multiple times, is the automatic export of that connection stiffness to the global Rfem model. But we're also working on AISC HSS through bolt connections, as well as AISC base plate design. So we're just about ready to release this for Eurocode for base plate design, again, including FEA with our concrete block. Everything will be carried out just like what you've seen in today's example for base plates. So therefore, after we release the Eurocode, the AISC will be soon to follow. And then some other developments such as graphic display of dimensions just for easier component input. Modeling improvements, we're going to apply maybe easier insertion of members and plates. So we'll see this added within the steel joints add-on. And then probably more so underneath the hood is just calculation optimization. So better generation of mesh, the details, and in general, the performance of those submodels. And lastly, we are planning to completely overhaul this template library for all of our different connection types. We want to integrate them with the Delubal Center. So probably some major changes you'll notice in the near future once you update Rfem as well. So this presentation was recorded. It will be available on our website and YouTube channel. It will be listed on the webpage that you did register for this particular webinar. I've already put on there our example model from today, so you can download this same model. You can also access the 90-day trial version of Rfem that includes all add-ons, its full capability for 90 days. So you can download today's model, open it up in that trial version, and rewatch this video at your own leisure. If you have any questions about today's products or today's presentation or any of our products, feel free to contact us at our Philadelphia office with the information shown at the bottom of the screen. If you're interested in scheduling an online demo or you'd like to just have a quick call about Rfem's capabilities and how this may be relevant for you, our sales team would be more than happy to get that scheduled. This is a hyperlink in the PowerPoint attachment in the GoToWebinar, as well as now available on our website, as well as this QR code to reach out to our sales team. We would be happy to schedule that with you. We will have many more upcoming webinars. We hold these approximately once a month. You can register at delubal.com under support and learning webinars. As most of you know, I tend to send out a reminder email about a week before these take place, so just keep an eye out for those. PDH certificates will automatically be emailed to all participants who were here for the full presentation. So that is a requirement of the state. So we are pre-approved providers that you are here for the full 60 minutes in order to receive that PDH credit. If you did watch with a colleague or you watched in a conference type setting and you yourself did not register for this GoToWebinar, but you were here for the full presentation and are wanting PDH, you will need to request that by sending an email to info-us@delubal.com. So again, if you didn't register yourself, but you were here for the full presentation, go ahead and request that PDH through this email shown. The PDHs are not automatic as soon as this presentation ends. They're usually sent within the next day, so you can keep an eye out in your email for that. With that said, I want to thank everyone for attending, and as always, we hope to see you at our next presentation. Thank you.